Every time new hardware silicon hits the market, we all fall for the same old temptation.
Oh yeah, you stare right at the peak numbers, the theoretical maximums.
And then you just mentally multiply them by how many you think you can cram into a rack. It's almost a reflex.
It is. And it's, the comfortable but often misleading path because it allows you to completely skip the messy part.
The messy part being.
Well, the massive hidden costs. The places where real systems lose time, lose watts, and quietly lose money because of integration chaos, unpredictable latency, and just operational friction.
That friction is exactly what the stack of sources we're looking at today is designed to eliminate. We're going through the material on the NVIDIA Rubin architecture, announced in January 2026.
And the core idea here is a really strategic shift. The system integration itself, that's now the product.
Right. So what's so interesting here is that this is a system design bet, not just a single chip launch. The whole goal seems to be moving the unit of compute from the server to the entire rack.
Exactly. They're designing the whole thing, compute, networking, security, operations, as one coordinated, high-throughput machine.
And the pitch is simple. Building AI factories, repeatable, stable building blocks that are just designed to convert power and data into tokens, predictably, day after day.
So what we're going to do today is really explore that concept. We'll look at how performance stops being a single GPU spec and starts being a property of the whole system.
Especially for the kinds of models that are dominating now, right? The agentic, long context, and mixture of experts models.
And if you connect that to the bigger operational picture, this level of integration is aimed squarely at reducing those hidden bottlenecks that just destroy your throughput. The promise isn't just speed, it's predictability.
More stable performance, and maybe most importantly, a lower true serving cost, so measured in tokens per watt.
That's the real metric.
Okay, let's unpack that core philosophy then. If the rack is the new unit, what fundamentally changed in the design mindset?
Well, according to the source material, the one-paragraph version of the change is that Rubin takes components that used to be, well, loosely bolted together.
Things like the CPU, the fabrics, the NIC, the DPU.
All of it, the Ethernet switch. And it designs them as a single fully integrated platform. The intention is for this entire NVL72 rack to behave like one giant machine.
And the practical payoff of that kind of integration has to be huge for operators.
It is. Fewer hidden bottlenecks, that translates directly into far more stable throughput. And maybe my favorite part, less topology drama when you try to launch big parallel jobs.
Topology drama is a great phrase. For anyone listening, what does that actually look like in the real world for, say, an AI operator?
Oh, absolutely. Topology drama is when you launch a big distributed training job across maybe 10 servers, and because of subtle differences in wiring or switch latency, the job runs 50% slower on Tuesday than it did on Monday.
For no obvious reason.
For no reason you can easily debug. Or the job just fails halfway through because one server hits a bottleneck and times out the entire communication collective. By making all 72 GPUs peers in one uniform topology, they're just eliminating that massive source of variance.
That consistency is key for the whole AI factory idea. And the sources also mention security changes too.
Right. Security expands from a single device to the whole rack. It spans the CPU, GPU, all the interconnects. And expanding that trust domain makes deployment so much easier for regulated or multi-tenant workloads. That's where a lot of this is heading.
Which is why NVIDIA calls the system one AI supercomputer. The whole idea is to change what the scheduler's natural unit is.
Exactly. Historically, it was the 8-GPU server, and you'd stitch 100 of those together over external networks, and that often required heroic levels of manual tuning.
But now the unit is the rack itself, specifically the NVIDIA Vera Rubin NVL72.
Precisely. And inside that rack, the NVLink scale-up network is incredibly dense and uniform. All 72 GPUs are peers in one performance domain. This just gets rid of a huge class of parallel processing headaches.
And the operations angle feels baked in from the start. The sources keep emphasizing that when the rack is the product, things like serviceability, telemetry, cooling, they aren't afterthoughts.
No, their baseline features are part of the architecture itself, which signals that ops is no longer something you figure out later.
Okay, so let's get into the components. We have the marketing line, 6 new chips, but the more useful way to think about it is, what, 6 specialized roles?
I think that's exactly right. 6 roles that used to be crammed onto the host CPU or were just loosely coordinated. Now they're specialized silicon, all working together. It's about eliminating contention by giving every major function its own dedicated resources.
All right, let's run down the list. What's number one?
First, you have the NVIDIA Vera CPU, and it's really evolving into this intelligent data movement and orchestration engine. It's managing the control flow for the whole system.
Okay, and then the GPU. The Rubin GPU is still the execution engine for compute and memory traffic, right? That's what's making the tokens.
That's the token generator. Then third, you have the NVLink 6 switch. And this is that crucial scale-up fabric providing the dense, high-speed connectivity that unifies all 72 of those GPUs.
Making them act as one.
Exactly.
And this is where the integration really starts to matter, because we have the Connect X9 SuperNIC and the Bluefield 4 DPU. Now hold on. For the listener who might be focused just on GPUs, what exactly is the DPU offloading that the main CPU can't handle?
That's a great question because the DPU, the data processing unit, is maybe the biggest strategic infrastructure piece here. The Bluefield 4 DPU is an infrastructure processor. It's dedicated to running system-level tasks.
So networking stacks, storage management.
Security, telemetry, all of it.
Yeah.
It offloads all that infrastructure work so the high-value Vera CPU and Rubin GPUs don't waste any cycles on basic housekeeping.
So the SuperNIC is the main highway out of the rack, and the DPU is like the traffic controller and operations manager inside.
Perfect analogy. The SuperNIC is the scale-out endpoint for that predictable cross-rack traffic. The DPU ensures that all the internal stuff networking, storage, encryption doesn't fight the main AI workload for resources.
Okay, and the sixth piece?
And finally, number 6 is the Spectrum 6 Ethernet switch silicon, which is paired with Spectrum X Ethernet photonics. This is the network silicon that's heavily focused on power efficiency and uptime for the whole fabric, especially at huge scale.
The source material has a great line for this. It says, the GPUs make the tokens, but the rest of the stack, those 5 other roles, makes token production repeatable.
That one sentence says it all. System stability and predictability are now the highest priority.
Okay, so let's shift focus to the compute itself, starting with the Vera CPU. Because the GPU does the heavy lifting, but modern inferences, it's changing, isn't it?
It is. We're dealing with what they call agentic work, multi-step reasoning, tool use, retries, all this complex control flow. And that requires constant state management, which is exactly where the Vera CPU steps up.
And the technical key here, the thing that really impacts the serving fleet, is the introduction of coherent memory via NVLink C2C. How much latency does that really save when you're juggling huge context windows?
It's a game changer for state management. Coherence means the system can treat CPU memory as a true, consistent extension of the GPU's working set.
So no more slow, costly memory copies.
Exactly. Before, moving data between the CPU and GPU was expensive. It created all this overhead. By getting rid of that, the CPU isn't playing catch-up anymore. For busy serving fleets, that coherence just drastically improves efficiency and lowers the power burn during those transitions. It's a huge relief.
And that focus on efficiency is critical. Rubin is being sold on the economics of tokens per watt, not just raw speed.
Right. By moving data more efficiently, the CPU reduces what the source calls the parasitic energy spent on everything that is not generating tokens.
I love that phrase. So moving to the Rubin GPU, the advancements there seem focused on improving the cost structure of inference.
Primarily, yes. You see the continuation of low-precision math with NVFP4 and the third-gen transformer engine.
Which is all about packing more useful work into every joule of energy without wrecking accuracy.
And that leads directly to cheaper inference. You either get higher throughput at the same latency or the same throughput for way less energy.
Then the second big advancement is on the memory side with HBM4.
Which is a direct attack on the bottleneck for long context. Long context is fundamentally a memory traffic problem, dealing with all that attention overhead.
So when you raise that memory bandwidth ceiling, you get smoother interactive serving.
And large context stops being a niche, expensive feature. It just becomes the default way you operate.
So if HBM4 fixes the memory problem, what was the next biggest bottleneck they had to solve to make this work at a massive scale?
It connects right back to the system architecture. The third point about the GPU is that communication is now part of GPU performance. The raw speed of a single GPU is meaningless if it can't share data quickly.
Right, because modern jobs are so distributed.
So the GPU is now shipped with an integrated scale-up story. The interconnect isn't an accessory anymore. It defines the performance you can actually achieve.
And that brings us right to the intelligent fabric holding the rack together, the NVLink 6 switch.
That's the essential glue. Its design goal is to deliver uniform, all-to-all connectivity across that whole NVL72 rack. It ensures that communication patterns, like for MoE routing, don't certainly hit some unexpected cliff in the topology.
The practical payoff for an operator there is just higher utilization and way less variance. If you've ever had to write those heroic workarounds in software just to manage communication.
You'll appreciate this. The hardware now treats communication as a first-class workload, not just some overhead you have to deal with.
But the work doesn't end inside the rack. When we scale out to thousands of racks, the ConnectX-9 SuperNIC takes over.
Right. It handles the external challenges. Managing congestion, keeping tail latency low, and smoothing out those synchronized bursts of traffic that can just flood a network.
And that's especially important for MOE models, isn't it?
It's vital. MOE Expert Dispatch is inherently bursty. It sends data in these sudden synchronized spikes. The SuperNIC basically makes standard Ethernet behave like a serious AI fabric by controlling that traffic right at the edge before the switches get overwhelmed and turn into a traffic jam.
Then there's the reliability piece of the network itself. That's the Spectrum 6 Ethernet switch and the Spectrum X photonics.
At extreme scale, the network becomes a primary reliability problem, just the sheer number of physical parts. Spectrum X aims to cut the power use and failure rate of the optics, the transceivers and retimers.
And if you're running a large fabric, you know that high failure rates on optical parts means network uptime becomes your bottleneck.
Exactly. And this focus also supports that scale-across idea. It makes multi-site AI factories feasible because the fabric can behave predictably even across multiple buildings.
Let's circle back to the Bluefield 4 DPU. Its role as an infrastructure processor is, it feels quietly radical. It's giving the control plane its own dedicated silicon.
It's fundamentally a stability strategy. Offloading all that work, networking, storage, encryption, telemetry onto the DPU is about separating concerns.
So the main CPUs aren't trying to run the AI workload and the infrastructure at the same time.
Right. When they do, you get contention in all these weird failure modes. By separating them, system performance becomes so much more deterministic. The high-value GPUs are truly just focused on making tokens.
One of the most fascinating ideas connected to the DPU is this concept of inference context memory storage, treating the KV cache as a shared resource.
And for anyone listening, the KV cache is the memory that stores the history of the conversation in an LLM. If you drop the session, you have to rebuild it from scratch.
Which is a huge waste.
A massive waste. This is pure AI factory thinking. In these long, multi-turn agentic systems, instead of constantly rebuilding that state, you persist it and reuse it across the whole fleet. It raises throughput, it cuts latency, it just stops the system from constantly forgetting what it just did.
And finally, we have the unglamorous but essential parts. Confidential computing and RAS reliability, availability, and serviceability.
The rack-scale confidential computing expands that crust domain across everything. And this is the difference between an organization being able to say, yes, we can run this sensitive model in the cloud safely, versus their legal department saying, absolutely not.
And the RAS engine.
The RAS engine is there to protect goodput, the actual amount of useful work you get done over time. The goal isn't just fast restarts when something fails. It's aiming for not needing restarts at all.
Okay, so we have to address the headline claims. Up to 10x lower cost per token, 4x fewer GPUs for MOE training. We have to caution the listener here.
Absolutely, we have to. These dramatic gains are workload-specific and they're end-to-end. You only see those kinds of multipliers if your existing pipelines were bottlenecked on exactly what Rubin is designed to fix.
Communication, long context, memory pressure, ops overhead.
Precisely.
So give us a real-world example. If I'm running a basic vision model on this hardware, am I going to see 10x?
You absolutely will not. The 10x cost per token claim is tied directly to highly complex sustained inference workloads. The 4x fewer GPUs for MOE is achievable because that dense internal fabric drastically cuts the waste from communication in those bursty distributed models.
So the platform hits those specific pain points directly.
It does.
So the punchline really is this. Rubin raises the ceiling for peak performance, sure, but its main goal is raising the floor for predictable, stable performance.
Right. If your pipeline is bottlenecked on, say, data prep or storage, this architecture isn't going to magically solve that. It solves the communication and state management bottlenecks.
So looking ahead, partner availability is slated for the second half of 2026. As this hardware deploys, what are the key signals we should be watching for?
There are three, and they go beyond the initial marketing numbers. First, we need to see end-to-end benchmarks.
Real-world stuff, interactive inference at a fixed latency, MOE training with real bursty routing.
And the final cost per token once you factor in power and facilities costs. That's the real number.
What's number two?
Second is software maturity. This amazing hardware is useless if the AI frameworks and serving stacks can't use it. We need to watch how quickly they standardize around efficient sharding, new communication collectives, and critically, the reuse of that shared KV cache.
And third,
Third is the reality of power, cooling, and pricing. These are the true modern constraints for any data center expansion. We need to watch how these high-density racks are actually deployed and what the real total cost per token looks like when the facility requirements are on the final bill.
that's what tells the whole story of its industrial success.
It does. I mean, at the end of the day, the Rubin architecture is this industrial-scale bet on predictable token production. It's shifting the focus from individual component specs to optimizing the entire system stack. This is what the architecture of an industrial-scale AI factory really looks like.
So what does this all mean for the future? If communication is now integrated hardware and operations are a baseline feature of the silicon, what does this shift mean for the kind of talent that's needed to manage these AI factories?
That's a great question.
Is the AI engineer becoming more like a factory floor manager, focusing on utilization, uptime, logistics, and power efficiency, more than just being a pure code jockey?
It feels like it's heading that way.
We'd encourage you to think about how this highly integrated architecture aligns with your own workload, whether that's heavy MOE training, long context serving, or multi-tenant inference, and what new operational bottlenecks this level of integration might finally allow you to tackle next.